Today we're going to continue on our journey of acids and bases. We're going to talk about this. This topic is arguably the most applicable, the most everyday life, the most useful, most important, I guess, part of the unit. At least in terms of leaving the chemistry course. So as a quick do now to get you started, just take a look at this. This should be very reminiscent of the last lesson you had. Just take a second. I added a slight tweak to it. Identify the acids, just the acids, in either side of the equation. I meant to make this an equilibrium arrow. I can make this an equilibrium arrow now. And the time it takes me to make this an equilibrium arrow, you should be able to identify the acids. There we go. So even though there are sodium ions present, remember that sodium compounds are always soluble in water. So it's almost like the sodium ions can be ignored. They're a spectator, if you will. So it's more important to look at the hydrogen ions, and what they are doing. This substance has one hydrogen, this substance has one, this substance is 0 afterwards, and this has 2. So clearly a hydrogen moved that way. That would make this the acid, and then working in the reverse direction it would move that way, so that makes this the acid. Moving on into today, I just wanted to show this because this is an image you can find on Google. It's an image you can find in a textbook. There are all these scales of the pH and whether or not something is an acid or a base or acidic or alkaline. But hopefully just even looking at this and thinking about it for a second, your brain should go, wait a second, but what is pH? How is it measured? How does it actually relate to acidity? And that's what we're going to take a look at today. Specifically, what is pH and how is it measured? I'm going to say that this scale isn't 100% my favorite. None of the scales are. This one's pretty good because most of these substances are kind of fixed. But I think the biggest misconception that people have about pH is that, yes, bleach has a pH of 13. No, it doesn't. The bleach that you buy in a store comes at a certain concentration, and that concentration will yield a pH value of about 13. Same thing with like stomach acid. The contents of your stomach change over time. If you drink water, the concentration of what's in your stomach changes, and then the pH of your stomach contents change. By drinking water, I've shifted the pH slightly. So you can't just say, stomach acid is a 1. But we'll start by building up the scale, and then maybe you'll see what I mean by the end of this. To get into pH, though, I think the first thing to consider is the autoionization of water. In any sample of water, you have your beaker, and there's lots and lots of H2Os, obviously, all these H2O particles. Well, we established in our previous lesson that water has the propensity to act as an acid or a base. And on the homework sheet I put up, you even saw in a couple of reactions that it did that with itself. What we see is that there is a chance that two water particles can collide with sufficient energy and sufficient orientation to have one of them act as a base and one of them act as an acid. This is in equilibrium because obviously those two particles could then recollide, and then they could recreate the waters, and so this is constantly happening. But if this is an equilibrium and it's constantly happening, that means there's a constant concentration, and that's what equilibrium means. And so if we can figure out that constant concentration, that might yield some information because, and we'll get to this in our future slides, acids and bases are identified by those two substances right above my head. So it's really more fair to say that in every sample of water, there is some H3O plus and some OH minus. But how much? And it turns out there's a way to measure the amount present at equilibrium. It involves something called an equilibrium constant, and I'll just give you the one for water because it's an important one. It is always true for any aqueous solution, which, of course, all of these acids and bases you saw on the previous slide, all of these are aqueous solutions. Every single one of them. Yeah, I'm looking at them just to make sure. Every single one of these is an aqueous solution. As long as there's water present, this is happening. This equilibrium is taking place. And for all water, the concentration of H3O plus times the concentration of hydroxide is always equal to 1 times 10 to the negative 14th. Some of your textbooks will refer to this as Kw, constant for water. Remember that this is also H plus times OH minus is equal to 1 times 10 to the negative 14th. Since if you were considering a substance or a pure water, right, not a substance, or substance, water, based on the chemistry of this equation, the concentration of hydronium and the concentration of hydroxide have to be equal. Conservation of matter says if you create one hydronium, you have to create one hydroxide. One H plus moves from one water to another, you create one of each particle. Well, that means if we're in pure water, we can say they're equal to each other. And if we wanted to, we could just call that, say, x. In other words, x squared equals 1 times 10 to the negative 14th, and then x equals 1 times 10 to the negative 7th molar, which is 0.000001 molar. So this drawing doesn't really accurately represent the number of hydrogen ions and the number of hydroxide ions in water, but it gives you an idea. It's a small number. I mean, I'm not equating this to a parts per million or anything like that, but roughly that's 1/10,000,000th, or if you wanted to say it this way, like roughly 1 in 10 million. So at equilibrium, for every 10 million water molecules, you have one hydronium. Which is not a terribly large number. I mean, yeah, a mole of water is a lot more than that, but like, there's still, the solution is vastly, vastly water and nothing else. But this number is very important, and I'm sure some of you are looking at this going, wait, there's a 14 there, and there's a 14. What? That's super important. So before we get into measuring pH of acids, I wanted to take a second to talk about logarithms. Of course, everyone's at a different point in their math classes, especially now. But some of you are taking trig, some of you are not taking trig. I just wanted to fill in the blanks. So a logarithm is a function. It's plain and simple, which means plug in one number, perform function, get out other number. So what I have here is I have 4 different numbers and their logarithms. Hopefully we can see the pattern. Hit the pause button. Think about it for a second. Try and figure out the pattern between what happens to x and what happens to the log of x. Okay, so you can probably see this, right? This is a change of times 10, and this is a change of plus 1. This is a change of times 100, and this is a change of plus 2. So it's a function. I can describe what the function is. I mean, for most situations, you can just think of it as a button on your calculator, and it performs the function for you. But in simple definitions, a logarithm is what power do you have to raise 10 to get x? In other words, x equals 3.59, log of x equals 0.555. that means 10 to the 0.555 power equals 3.59. It's just another way of writing this exponent in a way where you're kind of starting with the answer instead of starting with the exponent. I don't need to get any more into it than that. The only reason I talk about logarithms as a function is this relationship is really important, where a logarithm works by taking your input values, and for every power of 10, you only see a difference of 1 unit. So it really condenses down massive changes. And the reason I say that is that the function p is an operator. Lowercase p in chemistry, elsewhere, means negative log of. So px equals negative log of x. I guess for those of you who are already working with logs in your math course, yeah, it's possible to measure the log of a different base. We use base 10 especially for the p operator. Yeah, you can use a different base, and there's change of base formulas. I'm not getting into that. I'm only working in base 10. So, looking at the same x values for the first two columns, we notice that if the x value gets 10 times larger, the px value decreases by 1. If the x value gets 10 times smaller, the p value increases by 1. And the reason you see that is because there's this negative here. And then if you can also compare here, if the x value gets 100 times smaller, the p value gets increased by 2. So for every power of 10, it's 1 unit. Now, why am I taking the time to describe this function p? Well, you can apply the function p to anything, and in chemistry we do this because, especially when you have really small concentrations, it helps our brain understand what we're looking at. You might have seen this when we talked about like moles or unit conversions or like parts per million. We frequently manipulate our numbers to make them easy for our brains to digest. So you can measure the p of anything. So pH would be negative log of the H plus concentration. You could also measure, if you wanted, pOH or pNa or pCl, I don't know, whatever you want. And there's probably reasons that people would look at each of these, but in terms of acids and bases, since acids and bases is so heavily focused on hydronium concentration, measuring the pH is a natural progression. So how does that actually get implemented? Well, let's look at some solutions. First, let's take our HCl, our standard hydrochloric acid solution. We want to figure out the pH of a 0.100 molar solution. So the first question I have to ask is, well, what is the H plus concentration? We know that hydrochloric acid will react with water in a one-way reaction to make H3O plus OH minus, or wait, I'm still stuck on the KW. Okay. Cl minus. So in a 0.100 molar solution, this doesn't really exist because it's a one-way process. And that means that this concentration is 0.100 molar and 0.100 molar. I think we've talked about this with moles in general. 1 mole of sodium chloride contains 1 mole of sodium and 1 mole of chloride. So a 0.1 molar solution of HCl would be 0.1 molar H plus and 0.1 molar Cl minus. So in this solution, the hydronium ion concentration is 0.100 molar. compared to pure water, how does adding HCl to water affect the H plus concentration? Well, don't forget, we had this reaction already that takes place. Forgive me if I eventually move away from the writing all the phases in the... Oh, you know what? I can write them in. Why not? In this reaction, equilibrium already exists. That's what water does. So if you add the HCl and that increases the H plus concentration, well, that's a stress. If we increase H plus, what's going to happen is you'll see a shift left. And what will happen is, yeah, this will go down, but more importantly, the hydroxide will go down. Now, this is where I'm going to try and avoid a lot of the math. It would probably invoke a quadratic equation. I don't want to do that. Let's just say that the decrease in the H plus concentration is negligible. And I'll show you why. Oh no, actually, let's not worry about it. Let's just leave it at this for now. This is the important observation to make. As H plus concentration increases, OH minus concentration decreases, and we know that because it always has to multiply to equal 1 times 10 to the minus 14th. That'll come into play on the next slide. But what is the pH of the solution? Well, to find the pH of the solution, it's actually fairly straightforward because we know what the H plus concentration is. So all you have to do is say pH equals negative log of 0.100. And if you grab your calculator, you calculate that, what you get is 1. And I will show how that gets a little bit simpler to manipulate in a little bit. But that's our answer right there. So, yeah. I think everything we need is circled in whatever color this is. I'm going to assume it's green. Yes. Now, if we wanted to figure out the pH of a base, this seems a little bit counterintuitive because we know that sodium hydroxide will dissolve to make Na plus OH minus. If we wanted to figure out the pH, how do we figure out the pH when there's no H? I don't see any H's. I see hydroxides, but I don't see any H pluses. Well, the easiest way to figure out pH, as long as you don't forget that this is aqueous, there is water present. And the presence of the hydroxide, just like we saw on the previous slide, the presence of the hydroxide impacts the hydronium, just like the presence of the hydronium affects the hydroxide. So we know that in a 0.010 molar solution of hydroxide, or sodium hydroxide, that the hydroxide ion concentration is 0.010 molar. That's the same thing that we saw with the HCl. We also know that because there's water present, the product of the H plus and the OH minus concentrations always has to be 1 times 10 to the minus 14th. Now we said before for pure water, H plus and OH minus are equal because of stoichiometry. Here, it's not pure water. There's a lot more hydroxide because someone dropped in a bunch of base. Yeah. Which means we now know that not only are they not equal, we know what one of them is. We know the hydroxide ion concentration, and we can plug that in. So 1 times 10 to the negative 14th equals H plus times 0.010. H plus is equal to 1 times 10 to the negative 12th. And if you plug that into your calculator, pH equals the negative log of 1 times 10 to the negative 12th, which is equal to 12. Now this is consistent with what we know about bases. We said that the pH of bases is greater than 7, and well, last time I checked, 12 is greater than 7. Now this is weird because this suggests that even in a basic solution, there is still H plus present. And so there's a bunch of conclusions we can draw about that. So let me go back to our slide and draw a couple conclusions. So now given what we're looking at here, we can actually say a couple things. We know for neutral that the concentration of H plus equals the concentration of OH minus. And we know in acidic solutions, all that really means is that the concentration of H plus is greater than the concentration of OH minus. As you add an acid to water, the hydronium goes up, and because of equilibrium, the hydroxide goes down. And in an alkaline solution, that doesn't mean just hydroxide. All that means is that the H plus concentration is less than the hydroxide ion concentration. You add base, the hydroxide ion concentration goes up, the hydronium concentration goes down. And you can actually make all of these relationships in a pretty straightforward fashion. We also know, there's one more thing to say. We also know that if the H plus ion concentration goes up, right, they were equal, now H plus is greater, that also means that the pH is going down. And if the pH goes up, that means that the H plus concentration goes down. This is consistent with what we saw with our X values here. As the X value goes up, the pX value goes down. As the X value goes down, the pX value goes up. So lots of extensions to be had here. There's a lot to be said. For the Regents curriculum, we're really going to try and make things as simple as possible. So I don't know if you noticed this on the previous slide, but there's a little pattern that I noticed I wanted to show, point out, accentuate even. It's wrong green. It's this. Now, some other people will refer to pH as the power of hydrogen or the potential of hydrogen. Since it's based on logarithms, logarithms are directly related to powers of 10, right? We said what a log was, and that does follow through. So one of the extensions of pH is we see that pH is the negative log of the H plus concentration. You can rewrite that to be 10 to the negative pH equals H plus. That's just applying the logarithm rule. This also means if the concentration of H plus is equal to 1 times 10 to the negative x, pH equals x, which is what we saw here. If you can write your hydronium ion concentration as 1 times 10 to the negative something, then the pH is the positive of that something. We see when you perform the p value, like the p function on non-1 values. This is not 1 times 10 to something, it's 3.59 or 3.59 times 10 to the first or 3.59 times 10 to the negative first. The pH, the px, is not a whole number, and that's okay, but you can still use that application here to convert back to your H plus concentration. You won't be expected to do that because, well, I keep saying non-graphing calculator, and if you have a 4-function calculator, I kept saying that was okay. So you won't be expected to do that on any of my tests, on any of the Regents or the SAT too, but it's good to know that that exists. So if H plus is equal to 1 times 10 to the negative third molar, pH equals 3. If it's 1 times 10 to the negative fourth molar, pH equals 4. If the H plus was 2 times 10 to the negative third molar, I would guess that the pH is in between 3 and 4, logically, based on what we can see, because the p-value is in between the two. You can also relate pH and pOH. This equation that we wrote here, and that I keep repeating, if you perform some logarithmic magic to it, you get this. And this would be a potentially much faster way to solve the previous problem. If the hydroxide ion concentration is 0.01 molar, this also means that you could convert this to a pOH of 2. And if pOH is 2, and pH plus pOH is always 14, then you can get to your 12 that way as well. So a couple things are, no, that's about it. So everything we said about pOH, or everything we said about pH is also true of pOH. As hydroxide ion concentration increases, the pOH goes down. As pOH goes down, pH goes up. So like there's all these like seesaw-like relationships going on. So just to sum things up, pH equals the negative log of the H plus ion concentration. The H plus concentration times the OH minus concentration equals 1 times 10 to the negative 14th if water is present. As H plus goes up, pH goes down, and then there's a bunch of relationships that come out of that. We said that pH plus pOH is equal to 14. There's a couple more things I want to say about a summary. The initial picture I showed you showed a scale from 0 to 14. That's really a boundary. It's not a hard boundary. It's a boundary for like biological systems. But I know that concentrated hydrochloric acid, the maximum saturated, is 12 molar. So hypothetically, you can make a 10 molar HCl solution. And that means that you would have 10 molar H plus. So the negative log of 10 equals negative 1. So your pH would be negative 1. It is possible to have negative pHs. It's possible to have pHs above 14. It just really needs really high concentrations of either acid or base, right? We have this here. You could have a pH of 0. You can have a pH of negative 1. You could have a pH of negative 2, but that would be a 100 molar HCl solution, which can't happen. But that leads me to my last point. For each pH unit change, H plus changes 10 times. 2 becomes 100 times, 3 becomes 1,000 times. And I think I just wrote behind my own head. But if we combine this statement and this statement, we can kind of make statements about any solution. Thanks for watching.